Try to go right. 1%, then increase the charges. When I do all, make sure the all. No, other way. And should the it's not. All right, so we have to explain what happening here on the graph, right? So what happening here on this graph? Already? Right, so right here. So imagine you have somebody like this starting at A. But let's call it O. Right? And the person walking, we just want to see how his journey changing, right? So he's starting at the origin, and then he moving away at distance S in a time T1. Y'all seen that? So he starts at time is 0, distance is 0, and he walk. Let's say he reached somewhere here. Let's say he reached somewhere here, right? And the displacement is S. So he start here, then he reach here in T1 seconds. Right? But while for him to reach from here to here, he has to move, right? So what he'll have? A what? Speed, a velocity, acceleration. What do you think? What will he have? Displacement, right? Changing with time. So his displacement changing with time. So he will have a velocity. But it's a straight line. So how much velocities he'll have? 1 velocity, 10 velocities. If it's a straight line, it means that you'll have 1 constant velocity. So from 0 to T1, he is moving with. From 0 to T1, he is moving with constant velocity. Right? Because it's displacement changing with time. So what you will learn is that if I were to find the gradient of a graph like this, I will be finding the velocity. Right? So if I gave you a displacement time graph, the gradient is velocity. You'll do this exact same thing in maths, huh? Exact thing in maths. What do you think is happening here? There's a horizontal line, right? There's a horizontal line. So between T1 and T2, is his distance changing, displacement changing? It's staying the same, right? So what does that mean? Time changing, but your displacement remaining the same. Constant what? He moving? Think about it. At this point, time changing, but S staying the same. Time changing, but S staying the same. Would he be moving? No. So between T1 and T2, here's stationary. Right? So if you see a horizontal line, it means stationary. What type of gradient is this here? This part here. There's a positive gradient. Is it up? And we said gradient is what? Velocity, right? Anybody remember what negative velocity means? What? Change in direction. So he means that he's moving in opposite direction. So he starts here, he reaches here, and now he's going backwards. because the displacement at T3 is 0. So if he start here, he went this way. When he reach here now, he went back the other way. That's what this graph is saying, right? Has nothing to do with going up a hill, staying on top of the hill and coming down the hill. This graph is showing you, you start from rest, he went to displacement S in T1 seconds. Between T1 and T2, he stayed right here, he took a rest. And then from T2 to T3, he walked back to the starting point. Okay, so moving in the opposite direction to the starting point. Right? What was wrong? Huh? Right, copy that one, please.
Hey. It's so beautiful.
Right, so again, let me just go over this to make sure you all remember this. Velocity tells you how displacement changes with time. Okay, so, and velocity is also a vector quantity, right? So therefore, one direction positive, next direction negative. Okay, speed is a scalar quantity. Acceleration is the change in velocity with respect to time. So here, we're moving with a constant velocity. So is the velocity changing? No. If your velocity not changing, would you have any acceleration? No. The acceleration in this journey is 0. That's okay? Now I'm going to give you a next type of graph. The next type of graph is I can use the same graph, right? Because I can't run up this, I'm using the same graph. Now, won't be distance, it will be velocity time. Right, so we're looking at something called velocity time graph. Let's see if we can figure out what's happening here on this journey here. Yeah. Who knows that? Right. So before you write anything, anybody could describe what happened from 0 to T1? Right. So there's a constant change in velocity, right? So from 0 to T1, moving with constant acceleration. So what does the gradient for this graph give you? So the gradient for velocity time graph gives you the acceleration. So from 0 to T1, they're moving with constant acceleration. What about T1 to T2? Constant velocity. Constant velocity. And the acceleration? No acceleration. What about T2 to T3? Deceleration. So acceleration, deceleration. What about area under the graph? Area under velocity time graph. That's how we find the. I give all this already. No? I'll do the maths. Right? That'll be the distance traveled, right? So the area under this graph is distance traveled. Okay? Right? When you finish, head up Newton's tree load. All right, let's see if I can get this submitted. All right, so before we look at Newton's laws, let's see if we understand what happened here in all these simulations, right? Online, you'll see that. Online, you'll see this simulation. Yeah, all right. So let's start here. Right, of course, this is what will happen here, right? Let me restart it. Let me bring somebody here. What would happen if force is equal? Right? It should move, right? It should stay right where it is, right? Force is equal. If you add Naya here to give a little help. So what will happen, right?
That's right.
That's okay? Right, now let's change up some things here now. Let's see, anybody knows Newton's first law? What is Newton's first law? Because we're going to try to demonstrate Newton's first law here. Right. So a simple way to look at it is if you apply a force to an object, it will continue to move in that direction unless a next force makes it behave different. So if I were to allow this red guy here to apply a force, this object will continue to move in the same direction. That's okay? Unless right? Unless an external force makes it behave different. So an object will stay moving in a straight line unless an external force makes it behave different. Okay?
Small red person.
Add a small red person here. Why? Those the inertia different, the inertia the pull still higher. All right, so that's how you look at Newton's first law. If you look at this one here, let's any friction here. Let's apply a little force. Right. What you'll recognize here, right, is that when you apply a force, the object moving. But look at this here. Let's go back to when the force was smaller. Right. So watch this here. He's applying a force of 37 newtons, but it's still going in the opposite direction. Now when it reaches okay, 100. Right now, it's going in the opposite direction. Why? Why that happening? Anybody can guess? Because we were applying a force and it was still going to the left. Anybody can explain? Anybody can explain why? Please start. Anybody can explain why? Watch it here again. I'm going to apply a force. 5 newtons to the right, 10. But now moving, why? Anybody can guess why it's not moving and he applying a force? Always start to move. Let's apply a smaller. Why it's not moving? Anybody can guess? Even F.
Friction.
Friction. right? There's friction on the ground. There's friction on the ground, and only when it overcomes friction, then you start to move. Right question. The applied force is to the right, right? What about where his acceleration is? To the right as well. What direction he moving in? Right? What is next one here? That could show you acceleration as well. You're applying a force, right? How much is friction? Right? So he bigger than friction, now it's time to move. What direction the acceleration in? To the right as well. Right? So Newton's second law, this is Newton's second law here. When you have an applied force, you'll also have an acceleration in the same direction. That's Newton's second law. You've seen it? Right? If there's no applied force, will the object move? No. Right? If there's no applied force, the object will not move, so there's no acceleration. That's Newton's second law. Newton's third law. Newton's third law on this one. Let's change the simulation. Newton's third law is the easiest, but you won't see it here. Can't get it wrong. Go with it with zero wrong. What's this one here? It's the third law.
This is a water jetpack, but no, that's not me flying it. This is me. It's part of what it looks, okay? But to understand how it works, we need to first talk rocket science. Rocket science is meant to be one of the most complicated things in the world, but the basic principle is incredibly simple. It's just Newton's third law. All forces come in pairs, which are equal and opposite. To demonstrate this, I'm using a fire extinguisher on a skateboard. As the carbon dioxide is forced outward of the extinguisher, it puts a force forward on me, causing me to accelerate. or that area. If you look closely, you can spot the exact moment I realized this is a fail. So what was the problem here? Well, the force applied to me by the carbon dioxide is equal to the rate of mass ejected out the back of the fire extinguisher, call it exhaust for short, multiplied by the velocity of that exhaust gas. So in this case, the carbon dioxide wasn't ejected fast enough to create a big enough force and overcome the small frictional forces to get me to accelerate. But it can be done, as has been demonstrated many times on YouTube. When the space shuttle lifts off, the exhaust gas will exit the nozzle at 3 to 4 kilometers per second, ejecting an amount of mass of 9,000 kilograms per second. This creates thrust equal to 30 million pounds, or the equivalent of about 2 million pieces of fire extinguisher. Now, imagine you're an astronaut trying to launch a space shuttle. You would be seated not vertically, but horizontally, perpendicular to the acceleration. That's because the human body is a little bit like a water balloon, where the water represents your blood and the balloon represents your other parts, like your skeleton. Now, if you're accelerated up really quickly, then your skeleton accelerates up at that rate, but your blood tends to stay where it is.
I know I get all of that.
Blood ending up in your feet.
But
Now, since there's
you
no
also the
oxygen
you also
in
the
your
application
brain,
is second law.
black out. But fighter pilots face an arguably worse fate when they accelerate down too fast, because then the blood all rushes to their head and they suffer from what's called a readout, where the blood actually comes out of their eye.
All right. Right, so we have 3 laws to look at, right? The first law, we call that the law of inertia. Wait, online, you're going on there now.
I was really.
So we have the first, second, and third law, right? So the first law, as I showed you earlier, an object will stay in a straight line unless an external force makes it behave differently. Next one, Newton's second law, is if there's a resultant force here, it will also have an acceleration in the same direction. And the third law, I don't know if you saw it there, let's say you have 2 objects. If this object applying a force here, then the next will apply an equal and opposite force. So for example, if you touch the wall, for example, the reason you can feel the wall is because the wall applying a force to you. That's the third law. If you apply it harder, what you will get? A much harder force being applied to you, right? So when you apply a force, an equal force is being applied back to you. All right. If your force is extremely large now, what will happen? On you, or you could break down the wall, right? So if your force is too large, then the object will experience that large force. It might give you back a large equal force, but what will happen is it might end up destroying the object. Like if you walk on sand, if you walk on ground, if you walk on this ground, will you leave a footprint? No. If you walk on sand, what will happen? So the force you applying is greater than the force being applied perfectly. All right, and that's Newton's third law. Okay, so we have 3 laws to write down. All right, so head up Newton's 3 laws, and let's write down each one of them. Not very much longer. I extend and we got stuff much with them.
No, we get full months. Yeah. We get a full month.
Newton's first law states that
On that one line. Next back up here. Okay, that's up. Right, Newton's first law states that a body at rest will stay at rest or if moving will continue to do so with uniform velocity, will continue to do so with uniform velocity, will continue to do so with uniform velocity in a straight line unless acted upon by an unbalanced force. Unless acted upon by an unbalanced force. First up, this law can also be explained. This law can also be explained by using the law of inertia. INERTI. Which states that the mass of an object is the measure of its resistance to motion. For example, I'm going to give an example of this in real life. What's an example of the first law? Oh, by the way, inertia is this, right? If I give you these two objects, right? Which of these objects requires a smaller force to make it move? Smaller object, right? And if it's moving, which of these requires smaller force to make it stop moving? Smaller one, right? So the smaller the mass, smaller the inertia. Bigger the mass, the bigger the inertia. That's okay? What's an everyday example of this? Yeah. What's in a car? And what will happen? All right, you close it, right? But if you use vanilla example, right? If you're moving in a car, right? And as soon as the mass breaks, for example, and you move forward, and you continue to move forward, unless you pull yourself back or you have on your seat belt, right? That's even too slow. So if you're in a car and the car suddenly mash a brake, you'll recognize that you'll move forward, right? Unless some force pulls it back on. All right. So let's write an example now. For example, For example, when a moving car suddenly stops, for example, when a moving car suddenly stops, persons in the car will continue to move forward. Persons in the car will continue to move forward until the seatbelt pulls them backwards. Right? And just note that larger mass equals larger inertia. Larger mass equals larger inertia. We've done second law. Second law. Take a little break there. Right. Plenty. We've done second law. Right, second law now. Time up. Right, Newton's second law states that. What is your final spelling? What's the word? What's the word? How many of us see?
Oh, yeah, that's in there. That's not in there.
What's your setup?
I just didn't so. The problem, that's such a promise.
Yeah, next one, somebody. All right, yes, Newton's second law states that the resultant force acting on an object, underline resultant. The resultant force acting on an object. The resultant force acting on an object is directly proportional to its acceleration. It's directly proportional to its acceleration. And they both take place in the same direction. And they both take place in the same direction. Right? Write this down for Newton's second law, F equals to ME. Right, Newton's second law, F is equal to ME. Okay, so that's Newton's second law and Newton's third law. Do I third law together? Okay. That's all I have to do. Right, write this down to third law. If body A, right, and then you can draw this diagram, right? If body A exerts a force on body B, if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. Okay, and then draw this and write this. Draw this and write this. Watch it, right? The force is equal, but what does the minus sign indicate? What does this mean? Opposite direction, right? So the forces are equal and the negative sign is opposite direction. Okay. Everybody okay with that? So Newton's first law of inertia. Second law, F equal to ma, resultant force equal to acceleration. And third law, F of a equal to F of. So I'm going to give you a scenario now, and you have to use one of the laws to explain it. All right? Try this one. Two students push two carts. Two students push two carts. Carts. Like a push a cart. Yeah. Two students push two carts on a smooth floor. Two students push two carts on a smooth floor using the same force. Using the same force. First up, one cart is empty. First up, one cart is empty and the other is loaded. Yes, well, I don't know. Oh, yeah. Did I get that question from the way? So two students push two carts on a smooth floor using the same force. One cart is empty and the other is loaded with heavy goods. Which cart will move faster and why? Which cart will move faster and why? Huh?
What's like?
Which line?
Those.
Oh, yeah, just stick up there. I could be wrong, but I think that's two that was doing the same thing then, put pools and all of the huge pen that do the same thing. Yeah, well, when you do your crap, I'm gonna get that.
No, I have to do another thing. I have to figure out what it is. You can yell about it.
Right, so you have to use the law or laws to explain what will happen. Would they move the same because they get the same force? No. Somebody will move faster, right? So we have to explain why. Using the law, you can't just say, well, person A will move faster. You have to tell them why. Make sure and state which law you're using. I have some more questions to give you about this. Don't know why. Will City. If what's up, we can which one? I mean, in teacher right? But it's still high, right?
I don't know.
Yeah, but I don't. This I better again. I would. I know. Staff will do. Now looking up. What's the next one now?
I agree.
I have which hybrid you picking up? 4 and 5, 2. Yeah, but I wouldn't look for me. That would just give you a other thing. So you have to see which laws you can use to explain it, right? Technically, it's all 3 laws in there. But to explain which are moving faster. Well, there are some codes to do. Okay, I see. I don't know why.
No.
Plenty and loud we are do all that.
I know it's a. You're ready.
Do that thing math, each one of the 3 people together.
I'll do number 1.
I don't want the first one last.
So what other we can do?
I only want to. I want to see how far it's fast.
Fine.
Which one will go? Right, so what you all use? Second, let's somehow now. So which one will move faster? The empty cart or the one with the larger? First one? Why? But why? It have nothing in it, okay, right? So the one with nothing in it will move faster, but why?
There's the box. Oh, the box. That's all.
Whatever explanation? No, nothing? But remember they said. But remember they said both applying the same force, but they getting close to it.
Well, if one have the
Any guess, Sasha? Huh? So what I mean? What will be larger? Because so the mass, you all said the mass small, right? So I'm gonna give you a little quick drawing here. That's the cart, right? So the cart has a mass and they have the same force being applied. That's okay? One of them, the mass is larger than the next one. So let's say M1 is larger than M2. And they both have the same force. Right? So we said the one with the smaller mass will move faster, right? So this one here moves faster. But I want to know why. Why it moves faster? Yes, the mass smaller. How come? Based on what you learned. How come? Okay, which law you use it? Second law, right? What you say? So if you use F is equal to ME, right? E is what? Right. So let's just make up some numbers. Let's say the force is 2 newtons being applied. Both are the same, right? Mass 1 bigger than mass 2. So let's say this is 20 kilograms and this is 2 kilograms. That's okay? Let's see if we can find the acceleration in both of them. Right? What's the acceleration of the first one? Force divided by mass, right? 2 divided by 20, that's 0.1. What about the next one? Force divided by mass. One is 0.1 and one is 1. Who will move faster? 1. Right? So the larger acceleration is with this one. So that's the explanation I wanted. Right? So write this down. Since the applied force was the same, by Newton's second law, since the applied force is the same, by Newton's second law, the acceleration of the lighter cart will be much larger. Right? So the acceleration of the lighter cart is larger, right? So we use Newton's second law. Okay? All right, take a 2-minute break again and then we continue. All right? Take a 2 minutes again. Right, start your back board now. Online, you'll see the whole board. Oh wait, I didn't. Oh, how much examples I gave it? Just one. Oh, wait, before I get a break, take this next one. I didn't give it a second one. Sorry. Write the second scenario down. A student jumps off a small boat. I supposed to give it two. Sorry. A student jumps off a small boat onto the jetty. A student jumps off a small boat onto the jetty. Full stop. As the student jumps forward, as the student jumps forward, as the student jumps forward, the boat moves backwards. Why? As the student jumps forward, the boat moves backward. Why? One of these laws as the explanation. Must use a law. Must use a law to explain it, right? Wait, you tell them. We gotta say why. I gotta write returns, whatever though.
But
Phenomenal thorough. Yeah, I'll take it. It could be anything, like, it could be a little board, a little circle board. Online system, which law you're using to explain it now? First, second, or third? Calling it a fool. Same thing on Saturday, same thing on Tuesday and Thursday. And Monday, Wednesday, Friday. I think. That's the way it's normally. And if I want to stay longer and do like have some hard questions, but we have time or to stay up Monday, Wednesday, right? So it's now you have to prepare for that.
it's Christmas. Summer vacation show.
Online is same thing. Which law you're using? Third law, right? We've done third law. So write this down. Wait, one more explanation. Huh? Okay, well, since. Probably.
Probably sensitive or people have right? So instead of jumping, safety was as it's pushing forward, it'll be out.
Right.
Uh,
Right? So when the person jumps on the foot, right? Yeah, seven. Right, so when you jump up foot, yeah, laugh with me. When you jump up foot, right? You both apply a force to him, and then he apply an equal and opposite force to the foot. But the problem is that the foot is on a what? The foot on the water, on a frictionless surface, right? So what will happen is that the boat wouldn't stop, the boat would just move on. All right, take a 4-minute break and then we go again.
how about this brief?
One more thing to do.
48 points.
5 minutes and then we start on.
Oh, that's the one.
No, it's 15. Minus 12, 26.
Yeah, is that 5 minutes?
That's cool.
4 minutes at a time.
That's second.
and the Pluto.
Huh?
What's up, Pluto?
The-
Pluto. Pluto Didi. Oh, what's it? What you say?
I spell it.
WORTN. Let's see what they. So yeah, that's right.
Yeah, I love
Okay,
that.
okay. Okay, let's go with. Let's go with this way.
Oh, yeah, I do.
Yeah, study like it, how to crack letters, and if you're in your right place, and trying to best do it.
Hola, Margarela.
Okay, let's go with. What, check it, check what.
Oh, the 4 minutes up. What it was?
What. We have one letter but not the correct place.
Oh, yeah, 1 letter.
Yeah, if it's correct, it's a.
Right. Great.
We have no E.
That's okay, so if we have any letters from it. Okay, we have an I. That's hard.
What are you doing?
No, it's.
Some of it. Yeah, but you have no plan.
Try on this. Okay, so where's that? Okay, and those are not the practices are in past. Yeah. Sun.
All right, I go back. All right, last thing I wanted to show you. Last thing here is your. Oh, wait, I went there. Okay. Okay. One is not, we will good solution. There you go again. All right, so we just focus on one new term, right? So if you look here, how can I take off the pick up one? What would happen if I allow these two objects to move? They'll collide, right? When these objects move, they have two things. They have velocity, right? They might have acceleration, but they have a new quantity that we call momentum. The symbol for momentum is P. Right? So the momentum of these objects is the mass of it by its velocity. So if I have a large object moving real fast, will have a bigger momentum than a small object moving the same speed. All right. So there's one more quantity that you want to add on here: speed, velocity, acceleration, and momentum. Momentum is the mass of the object by its velocity. You think momentum will be a scalar or vector quantity?
Vector.
Classical to them. They say what? Which one? Vector. Right? So based on the direction of your velocity, you'll be able to determine if the momentum is positive or not. Right? So what you say? Let's go back to this simulation here. If I were to press play, they collide. Right? They both have carry move one. I'm not sure if you'll see that. A little bit small. Right? What you would observe here is that, see the mass value here. So the blue has a mass of 0.1. What's that in? 805. And it has a velocity of 1, that's like 0.5. Right? So the mass of the blue is 0.5, the velocity is 1, and its speed is its momentum is 0.5. You see that? Right? So the momentum of this blue object here, light blue, sorry, whatever color that, teal. The momentum of this teal object is the mass by its velocity, which is 0.5. For the pink object now, the mass is 1.5 and the velocity is minus 0.5. So the momentum is the product of those two. You'll see that? You'll also recognize, I'm not sure if you've seen it, but a little sign in front there, which shows that it's negative. So when you move in this direction, momentum positive. When you move in this direction, momentum is negative. That's okay? So momentum is the product of both of them. All right? And because of that, because they both have momentum, right? They will move and they will collide into each other. So if I play right here, they'll collide and you will see them moving away. That's okay? Right? And that's our next law that we're going to learn, but I'm not going to show you that. I'm not going to show you that today. We just going to look at momentum today. Next day we'll look at change. All right? So let's do my favor. Head up linear momentum. Head up linear momentum and take this small thing here, right? Right? Take a small little bit for you draw this. The linear momentum of an object is the product of its mass and velocity. The linear momentum of an object is the product of its mass and velocity. right? And please note that is a vector quantity. Copy this down and you know. Oh wait, no, give out test. Oh yeah, go over. I know. But it just feels below. Alright, so that's momentum, right? So all the quantities that we did today will be speed, velocity, acceleration, and momentum, right? You have to be able to differentiate between all of them. Alright? You have to make sure you know which is which. Right? Which of those are scalar? Between speed, velocity, acceleration, and momentum. Which one? Speed. All the others are what? Right. Okay? Take this small example and be done. Example 1. A ball of mass 50 grams. A ball of mass 50 grams. It's moving with a speed. It's moving with a speed of 10 meters per second. When I choose that when I start a little bit, right? But the world go up and so it started, right? And I'm just doing the work for the day. Okay. But the second half, I'm gonna show them what we did.
It's really like commentary.
Yeah. But I will be just that a little bit too. Right, yeah. Find the momentum real fast. Just find the momentum and you're done. All right, so.
Mine's up. And
MIS. I was. right? Pay attention to the SI unit, right? Control that. So again, we're using momentum. The symbol is lowercase p, right? Momentum is mass by velocity. What's the mass? 50 grams, right? So that'll be 0.05 and the velocity will 10. So you should have gotten 0.5 kg ms minus 1. That's okay? Again, the main purpose of today's class is for you to understand the difference between speed, velocity, acceleration, momentum, and the three laws. All right? Before you go back to your second law, please. Go back to your second law. And I want you to squeeze this into your second law. Remember, we learned that what? F is equal to ma, right? And we learned that E is change in velocity. So I could also write it like this. Final velocity minus initial time. So if I squeeze it in here, watch what will happen. If I take up E and write this, I will end up with mv minus mu on t. Anybody can guess what you think this is? What is it? Well, remember, this is acceleration.
Gradient.
No.
Did you see it?
What this is here? What's mv? Momentum. So this is your final momentum, this is your initial momentum. So Newton's second law could be written like this. Change in momentum over time. So Newton's second law could be F equal to ma or change in momentum on time. Sorry to squeeze it up there, right? But this means change in momentum on time. So we're going to do a lot of questions on this next day, right? All right. So we'll stop there for today earlier.